All right, then one thing we need to consider is how do you take derivatives of trigonometric functions? So we're going to take a look at an introduction to that. The truth is there's no like one rule that gets you through it all. A lot of times with trig, what you're trying to do is you go through, you'll see sometimes we take things and we algebraically manipulate them to take another form. Sometimes you have some type of a insight into what you can do with it to get it to fit a certain way. Sometimes these problems can be done in more than one way, right? Because you've got so many choices in how you handle your trigonometry. So I have seen groups before of students who are working on taking the derivative of a trigonometric function, and they're working in a group of 4 people, and they might find like 3 or 4 different ways to do that same problem. So and this happens a lot in calculus, but especially when you start getting into the trigonometry, there are oftentimes different ways to do the same problem. So if you're looking at how I do this problem and go, well, why didn't he do it this way? Yeah, the way that you're talking about may be perfectly legitimate. So that can be both helpful and confusing, but just realize there's more than one way to do these problems, and you just get comfortable with whatever way works best for you. So here we have what hopefully you recognize as the sine function, and we're going to try to wrap our brain around what the derivative of the sine function would be. So what I'm about to show you is not necessarily like a rigorous mathematical proof, but it does give us enough insight as to why the derivative is what it is, that it really gives you something to fall back on when you're dealing with these derivatives and of trigonometric functions and you're kind of forgetting why they are what they are. If you can visualize it, a lot of times it really helps kind of bring that idea home. So that's how we're going to motivate to try to ask ourselves, what do we think the derivative of sine x would be? So that's the function that we're dealing with right here, sine of x. So let's see. The derivative is given to us by tangent lines. So usually what we do is we do the derivative to figure out our tangent lines. Here we're going to look at our tangent lines to see if it can help us figure out our derivative. So let's go ahead and put a tangent line on here, right? So that looks like a reasonable tangent line. So we'll start filling in a table over here for ourselves. Okay, so here's what it looks like when I bring the functions in so we can follow along exactly what I'm doing. We've got our red function, which is f of x equals sine x, and we can see that doing exactly what we expect it to do. And then I've got my I've got some parameters here so you can't see all the work generating this tangent line, but I've got our tangent line set up so we can see them actually moving along our sine function. So at any given point along the sine function, we can go through and see what that tangent line looks like it should be doing. So let's start here at 0. So these purple dots should be things that are on the derivative because the slope of the tangent line gives us a derivative. So by looking at the tangent lines, we should be able to make a connection to the derivative itself. Well, it looks like here at 0, that looks like our slope is 1. So I'm going to put a 1 here, right? And you can notice it's starting to plot points that fall on our derivative. Right? We're actually generating the derivative. And if we wanted to get really specific about this, we could plot a lot more points, but that would be a little bit messier. Okay, so then what are those tangent lines doing? We want to take a look at what that tangent line is doing as we move forward, as we're going this way. Okay, so it looks like that we said it looks like that tangent line is 1 originally, but what's it doing? It looks like it's decreasing. It's decreasing as it approaches the top of that hill, and then at the top of the hill it looks like that line should be right at 0, right? That tangent line, the black line we're looking at, should have a slope of 0. So it looks like as we move along this curve from 0 to pi halves, our tangent lines are reducing from 1 to 0. So it looks like this value looks like it should probably be 0. And then what happens, the slopes of those tangent lines continue to decrease as we go from the top of the hill down, as we move forward down to the trough, down to the bottom part. All right, it looks like we cross here somewhere right around pi. It looks like that would be -1. And then as we keep going, they kind of round out, and it looks like now they're actually starting to increase again. So the slopes of the tangent lines here is increasing. It's still negative, but it's getting less negative. So it's increasing up until the point where it looks like it bottoms out right at y equals -1. So it looks like we go through another period here where at 3 pi over 2, we get 0 again. So we can see these points being plotted. And then you can finish this out. So if we go forward, they start increasing. Now they're positive again, and it looks like they're going back towards 1. Now, what do we do with these points? We want to see if we can try to make sense of this. Again, if you wanted to, you could plot a whole bunch more of these, and you would start to see the shape even better. But this is just for instructional purposes. So if we get that line out of there and we start to look at this, you could say, oh, well, those make a V shape. That looks like the absolute value. That's a nice try from the number of points that we plotted. If we plotted a few more points, you would see that it doesn't actually end up working that way. We end up getting a kind of a curve. So it turns out that the derivative for sine is given by cosine, right? We can see all those points fit right on this line here. So in fact, the derivative of sine is cosine. So the cosine function really is giving you the slopes of the tangent line for your sine function. Now, unfortunately, it doesn't work the other way around. Sine is not the derivative of cosine. It's close, but not quite. So what you actually end up getting is this cycle where if you keep taking the derivative, you go sine, cosine, negative cosine, and then back to sine again. So the cycle takes 4 times to come back to the beginning, but then it just keeps cycling through, which is helpful. Okay, so with the trig functions especially, looking at the graph can be very helpful in trying to figure out what the derivative might be. But sometimes we are going to switch over it to being algebraic. For example, let's take a look here. We want to find the derivative of tangent x. So we've got our function tangent, and we want to find its derivative. Well, what would we do? Well, you could look at the graph like we did, but sometimes you want to be able to show things algebraically so you're actually proving them. Well, again, this goes back to what I mentioned before. There is no exact right way to do all of these problems. Different people are going to do it differently, and sometimes you have legitimately 2 or 3 or 4 different ways of doing the same problem. But the easiest way to solve a problem like this, tangent x, is probably to turn tangent into the sine and cosine parts, because we now know how to take the derivative of sine and cosine, right? We just figured that out. And then we have the quotient rule. So writing tangent as sine over cosine means now if we bring in our quotient rule before and we know the derivative of sine and cosine, then this shouldn't be too bad. So you can actually recognize this form right here. Yeah, that looks like the quotient rule that we just recently learned, right? So you take your previous denominator and square that. So the denominator piece is easy. And then you just fill in the top pieces with the functions and the derivatives that match, right? So we're looking at, we've got g of x times the derivative of f of x, so that sine x becomes cosine x, minus, and then we've got the original function by itself times the derivative of the bottom function. So the derivative of cosine is negative sine x. That's where this piece is coming through. And then this gives us cosine squared x plus sine squared x, and this is going to happen all the time when you do trig. In calculus, you're going to have to be on the lookout for identities and stuff like that, ways to simplify your terms down. So in this case, cosine squared plus sine squared is 1. So we end up with this piece right here. And it's usually just more convenient to write 1 over cosine squared as secant squared. So the derivative of tangent x is secant squared x.